Right.
But the clue to doing these, and this is regardless of where you're at in BC Calc, you need to know how to do these. The clue is figuring out which technique you're going to use. Okay, and it's not always clear. Let's just write it here. In this one, we're going to use the first one we used. The integral is going to be an arc tan.
Right.
Okay? Because we know that when we take the derivative of the arc tan, we get something that looks like that. So just label that like that for the moment. Second one, very similar, only that looks more like the arc sine. So we're going to use the arc sine to do that one. And there are two formulas that I did not remember last time on both of these that make these two problems much easier. And I'll show them to you in a second. But first of all, what I want to do is I want to look at all 9 of these and figure out how we're going to do each one of them.
Okay.
3. What method would you use for 3?
Okay. I think that we would use arc sine again.
That's what I thought when I first looked at it. But notice that if you're used to u substitution, what are we looking at? We're looking at the derivative of u being in the numerator. The derivative of u is going to be minus 8x, but the degree of x is the same as what's in the numerator.
Right.
And when you're looking at that, you're going to use u substitution. And once you use u substitution, it actually is much easier than these first two. Okay? We'll go through each one of these if we have time. But number 4, we're looking at the integral of inverse sine. Well, I think what I taught you was log poet. You're using integration by parts.
Correct.
It's really not the best thing. For one thing, all of that means log, and all of that means polynomial. There's another one that is better.
Okay.
Lipit. Lipit. And the I stands for, what do you think? That's
inverse.
Log. Inverse trig function. Still have the polynomial, still have the exponential, and still have the trig function. So we still have all of our major function groups. It's a shorter word, lipit, and it applies to this problem. So we're going to do this problem how, number 4?
U substitution or?
Well, it's integration by parts.
Okay.
Where you have to define u and dv. Okay? So this one's going to be integration by parts as opposed to integration by partial fractions. Number 5, what am I going to
do? Integration by parts.
What's u going to be on number 5?
U would be ln x, and then dv would be x squared.
Remember, dv is always everything else. So dv can't just be x squared. dv is x squared dx. Yeah, you need that dx to make sense mathematically. Number 6, what are we going to use? What does it look like we're probably going to use?
Integration by parts.
And it's probably going to be iterative. By that I mean there'll be more than just one step because we're looking at an x cubed. This number 5 might have actually one iteration. I would expect the first iteration would bring it down to an x, and then the second one would eliminate it. Okay? So, number 7, what are we going to
do? Partial fraction.
Yeah, when you see a denominator that's factorable, so integration by partial fractions. About number 8?
I think same thing. Integration by partial fractions.
Okay. And number 9, we have not talked about this one before. I had to think about this for a bit before I remembered how you do this.
Yeah. I think, would you be able to factor the numerator and then separate the fractions?
Well, let's see. The numerator factors into x minus 1 times x minus 2. So you end up with nothing canceling.
Right.
No, what you do on number 9 is if the degree of the numerator is higher than the degree of the denominator, then you divide it. And what that's going to give you is a quotient and a remainder. And the quotient is going to be added to the remainder. So you'll then have the integral of two different things, both of which will be easy to integrate.
Okay.
Okay? So that's step 1 when you're looking at these kind of problems, is figuring out what method you're going to use to do it. Okay? Now, let me show you these formulas because where did I put them? Right here. Let me do a little bit of writing on these. In other words, if you've got the integral of, let's take the arc sine, of 1 over the square root of 1 minus x squared, well, that's pretty easy, right? That's just arc sine of x plus c. The difficulty is when they make it a little more complicated, like they put a 9 instead of a 1 in there.
Mm-hmm.
And they put a number in the numerator. Well, these handle all of those situations where the numerator isn't 1, it's u. In other words, if u is not x, if u is something a little more complicated, like problem number, problem number 3. Well, no, that's not even a use. Problem number 2. Look at the denominator. It's the square root of 9 minus 4x squared.
Right.
Okay. In fact, let me write that one up here and we'll apply it. Okay. So we're taking the integral of 3 over square root of 9 minus 4x squared dx. Now, you can use some really sophisticated algebra, and I mean really sophisticated. I can divide the top by 3, and I can divide the bottom by 3, and then I can make that 3 on the bottom read square root of 9, and then I can combine the two radicals so that I end up with the radical of 1 minus 4/9 x squared. But that's hard to remember exactly how to do all those things. So they give you this formula that I've circled right here. Okay?
Right.
And the very first thing let's do, and I don't see any reason why you would not always want to do this, take that 3 outside the integral.
Okay.
Okay? Because you can, and it simplifies everything. Now, once we have it in this format, where we have a 1 in the numerator, well, now we're looking at exactly this, right? What's A?
A is 3.
What's U?
U is 4x.
It's the square root of that. What's the square root of 4x squared?
2x.
That's U. Okay? Now apply it to this formula right here. So our answer is going to be the arc sine of U I got it backwards, of U, which is 2x
over 3.
Over A. And can't forget that 3 that we took out. That goes right in front like that. Now notice that it does not cancel with that other 3. That other
Right.
3, that's part of an argument of arc sine.
Right.
So you cannot cancel with that 3. But that should be the answer to that problem. But
Okay.
notice how much easier it is. In other
Yeah.
words, once you can get 1 in the numerator, then your a squared, you just take the square root of whatever that is. Even if that number was 8, then a would be the square root of 8. Okay.
Right.
So you can handle numbers that are not perfect square numbers. Okay. So
Okay.
let's apply it. Well, we're limited on time here. These 3 are the ones you have to know.
Okay.
I don't think they're going to make it any harder than that. You know, the arc sine, the arc tan, and the arc secant. Notice the arc tan has a 1 over a out in front.
Right.
And it still has the u over a. And the arc secant has the absolute value of u over a, and also a 1 over a out front. So anything that you're going to use inverse trig functions to answer the integral, you want these 3 formulas. Now, you have a book, right?
Yes.
You open it to the front cover of that book. You get all your juicy derivative and integral formulas. I can't tell you how frequently I refer to this page.
Okay.
Do you have it? Let's make sure you have it.
I don't have the book on me now.
Don't have the book at home? Okay. Well, it's Larson, Hostetler, and Edwards, calculus of a single variable, right?
Correct.
So I'm sure that the inside page is going to be the same. I can't imagine they would ever change that.
Yeah, no.
But
It definitely
I also have those same formulas on page 520 of my book, and that's what I actually have up on the screen here, is the last 3 formulas that I didn't know by heart when we were doing it the other day. And boy, if you don't know these formulas, it's hard to solve those problems.
Right.
So,
I have a question.
uh-huh.
Can we go over number 9 first?
Yes.
So, because I think that's the one I'm the most fuzzy on.
Absolutely. Yes, that's probably one of the hardest ones.
Yeah, because I can remember the arc tan and arc sine. Use substitution I'm good on, and I don't think we're going to get an inverse trig function on the test. This is the first time we've seen it, so
the way you divide, first of all, the way you divide polynomials is by long division.
Okay.
Whoops, hold on. And you'll see it becomes a fairly easy problem once you get the division out of the way. X plus 1 divided into x squared minus 3x plus 2. So you have to do this division. Do you know how to do this division?
I'm still kind of, I haven't done it since.
The methodology is pretty easy. You start with the x and divide it into x squared. That's step 1. Step 2 is you multiply the x times the x plus 1. With me?
Yeah.
Make sure you follow every step. You subtract, if you remember back to your long division days, we're going to subtract. So x squared minus x squared is always going to be 0, but minus 3x minus another x is minus 4x. Bring down the next term and repeat the whole process.
So then I'm going into 4x now instead of
into minus 4x. And you're only dividing that into that for starters.
Okay.
Okay? In other words, you're ignoring the 1 when you first do the division. Once you get a result for that division, then you do multiply it by the x plus 1. So I'm dividing x into minus 4x, which is minus 4. Multiply minus 4 times x always gives you the same term. Minus 4 times plus 1 is minus 4. Subtract again. What do you get?
0 for the 4x's,
Uh-huh.
and then -2.
No, and remember you're taking +2 minus a -4.
So minus and -4, so so +6.
Correct. That's your remainder. Okay.
Okay.
Now, the way you write a remainder is you can put a little r there, but the way you write it mathematically is I'm adding 6 divided by x plus 1. Got it?
Mm-hmm.
Okay, now the rest of it's easy. In other words, if that's what that is, and if I'm taking the integral of that, now I say it's easy because the integral of a bunch of things is the integral of each one of them. So that's the same as the integral of x minus the integral of -4 plus the integral of 6 over x plus 1. What's the integral of x?
X squared over 2.
Keep going.
And then -4x.
I'm sorry, I have 2 negative signs there. I don't mean that. That negative is out in front of the integral sign. I don't want it twice.
Okay, yeah, so -4x plus, would that be 6 ln x plus 1?
Good. Exactly. And I can just do it direct like we did, or I can take that 6 out of the integral sign and put it in front. And I just got 1 over x plus 1, which is natural log of x plus 1.
Right.
Plus c.
And then,
there's your...
okay. Okay, yeah, that's not as hard as I thought it was.
No. Once you do that long division, then it ends up being an easy thing. You just have to understand that when you do that long division, you end up with a quotient and a remainder.
So
with the being divided by that same x plus 1.
Okay, so with the long division, so if it's a term like x plus 1, say like x plus 3, I do the same thing and I disregard the +3 for just the dividing part,
Yeah.
and I just divide x into it.
Yes.
Okay. And then I divide, and then I subtract.
Here, I'm just going to give you a practice one.
Okay. Early.
Do this one.
Minus.
Give me the first term. Give me the first term of the quotient.
X would go into x squared once.
Okay.
So that's x on top.
Okay.
And then you subtract.
No, first, now multiply.
So you multiply x plus 3 times x.
Yes.
So then you get x.
That's the first time the +3 comes into relevance.
Okay, so then you get x squared plus 3.
X.
X.
Multiply right. X times 3 is 3x.
Right. And then so then you subtract that. So then x squared minus x squared is 0. And then -7x minus +3x would be plus negative. So it would be -10x.
Good.
And then I'm going into, so then it would go
down the next term. That's always the next step in long division.
So they bring down the +10.
Now repeat.
Okay, and then it goes in 10 times. X goes into -10x 10 times.
Oh, goes in minus 10 times.
Okay, minus. Oh, so yeah, I just put the negatives. I should make sure to say that. I apologize.
Okay.
So then -10 times, and then so then it'd be -10x. 3 times -10 is -30.
Okay, keep going.
And then it's subtract that, so plus positive, so that'd be 0. And then it would be 40 would be the remainder.
Okay, now how do I write that as part of the quotient?
You add 40 over 40 over x plus 3.
There you go.
Okay.
Okay.
All right, that's simple enough.
The integral of that is what you're taking, which is the integral of the x, the integral of the minus 10, and the integral of that, all of which are easy to find the integrals.
Right.
All right.
Okay.
Let's see. What's the next toughest one? Let's see. I think these partial fractions, you got those down?
Yeah, I got the partial fractions.
Want to do number 3 using U substitution?
Yeah, I think that one's the next hardest one, so let's do that one.
Or else this number 4, the inverse sine, that could be also.
Let's do that one if we have time.
Okay, so let's do number 3. We've decided we're going to use U substitution, so what am I going to make U?
U would be 9 minus 4x squared.
And I always write my U over here, because that's where I'm going to do my differentiation.
And then
so my integral, and first thing I do is the differentiation, du dx.
Right. So du dx equals negative 8x.
Okay, which makes du equal to negative 8x dx.
Right.
Now, you want to do it the way your school teaches you, or you want to do it the way I do it, where I take the steps and I solve for dx? Because what we're going to do in this thing is substitute. Every single thing we're going to substitute.
Right. I think
substitute for dx. So I kind of like, just for conceptually understanding it, I like solving this for dx. Let's just try it. I actually think it makes some of these easier when they use fractions that are kind of crazy, like minus 8x.
Yeah, I think it will make it easier on the test just for me to not make a mistake, like mentally.
Yes, I agree. And it's easy to make a mistake trying to do it that one step shorter way. Okay? Right. So now we're going to write an integral in terms of u. Now, I haven't done anything with the 3x yet, so I'm going to leave that there. How am I going to write the bottom?
Radical u.
Okay.
And then du.
Dx is what?
Dx equals du over negative 8x.
Okay. And that accomplishes what we absolutely have to do, which is to get rid of that x. You cannot solve an integral of u if you have an x in it.
Right.
And now the numbers are easy. We can take that negative 3/8 out if we want, just to simplify things. And I'm going to turn this into u to the minus 1/2 du. See what I did? Everything?
Yeah.
Okay.
Yeah.
Now that's easy to integrate. What's u to the minus 1/2, the integral of that?
That would be u to the positive 1/2 times 2.
Okay. And still multiplying by the minus 3/8.
Right. So the final answer could be negative 6u to the 1/2 over 8 plus c.
Right. Only the negative 6 over 8 reduces to 3 over 4.
Right. So negative 3 over 4.
Minus 3/4 u to the 1/2 plus c. And then you still got to go back in because you don't want to give your answer in u.
Right.
In other words, they gave you the problem in x. You got to give them the answer back in x. Okay.
Right. So
here's the answer. Minus 3/4. U is 9 minus 4x squared. And I can either leave that. I prefer leaving fractional exponents in calculus just because the radical sign is very rarely valuable. I mean, you very rarely use that. I guess you use it when you're doing inverse trig functions, but
right.
There's your answer right there.
Okay.
And it doesn't help to distribute. It helps a little bit, I suppose, to distribute that. No, you can't distribute it. This whole thing in parentheses is to the 1/2 power, so I cannot distribute that 3/4.
Right.
And this would be the answer. Okay?
Okay.
See if we can
Yeah,
meet up with number 4 here.
Okay.
Okay. Based on Lippitt, I'm going to do this integration by parts,
Okay.
which means I need U.
So U would be inverse trig.
Which is that? What is dV?
Would that be
Everything else. What is everything else?
just dx?
There you go. Which makes V equal to
X dx?
just X.
Oh, X.
In other words, I'm integrating both sides. When you integrate dV, you get V, and when you integrate dx, you get X.
Okay.
Over here, I do need du dx. Well, what's du dx of the inverse sine function? Think this.
Oh, would it be okay. 1/root 1 minus x
Squared.
squared.
Yeah. In other words, if you're just differentiating the inverse sine of x and not something more complicated like x squared or x plus 1 or something like that, then it's always this right here. Okay?
Okay.
So du is that. And I'm going to need du. Part of integration by parts. Remember that the integral of this thing is equal to uv minus the integral of what?
uv minus the integral of v du.
Voodoo. That's the way I remember it. Okay. Yeah. What's uv?
uv is inverse sine x times x.
Okay, I'm going to put the x in front just so that there's no... In other words, you frequently want to do that on these.
Just so there's no confusion.
Yeah, in other words, a lot of times you'll want to write it as VU, not UV.
Okay.
Yeah,
because it doesn't matter either way.
On the other side, it's quite confusing. Don't you think this would be fairly confusing if I were to do that? You don't know if that second x is part of the argument or what. So same thing with logs. When you have a log multiplied by a polynomial, put the polynomial in front of it, or e to the x, anything. Not so vital there, but okay. Minus integral of what?
Of voodoo. So x.
Here's du right there.
X times dx over root 1 minus x squared.
How are you going to do that integral? Because we're not done with the problem, and we can do this integral. Think this, right up there.
Would we do arc sine?
No.
Or use substitution?
Substitution. The most important thing you need to know about U substitution is recognizing when to use it. And what you're looking for is a pattern. We want to find something in the numerator that is the derivative of what we're going to let u equal to. Well, clearly we're going to let u equal to 1 minus x squared, right?
Mm-hmm.
And the derivative of that is minus 2x. So we'll be able to get rid of that x. In the same way we got rid of it when we did number 3. So number 4 is actually integration by parts combined with integration using U substitution.
Right.
Now, it's not the same U. Understand that. In other words, when I solve this, I'm going to call it U substitution, but it's not this U right there.
Right.
It's a whole different problem. I could call it Z substitution if I wanted to. I can use any variable I want.
Right.
But I'm going to still use U because I think it's still probably more understandable. And it's not the square root of that, it's what's in the radical, because then we'll have the square root of U and we can use the power rule to integrate that.
Right.
Okay, so du dx is what?
Du dx is negative 2x.
Okay. Which makes du equal to minus 2x dx. And it's really dx we need to solve for, so we're going to put that over there. If you want me to go ahead and finish up this problem, I'm happy to. I don't know if I'm cutting into your time or not.
No, you're fine. Yeah, we can finish.
Finished up. We don't have much more to go here. Okay, so now how do I write that integral in terms of u?
So put a negative 1/2 out front, and then
which turns that into a plus 1/2. Notice,
right?
Because we were subtracting that integral.
Yeah, so plus 1/2 integral of u to the negative 1/2.
Good. And did a couple steps in there. Du.
Yeah, du.
Okay. Now you can integrate that. That integrates into 2u to the positive 1/2.
Right.
And that 2 cancels out with this 1/2. So let's get rid of that integral sign. We don't need that. And we've got square root of u. And u was 1 minus x squared. And we don't need the du because we already integrated it.
Right. So then the final answer would be x inverse sine x plus radical 1 minus x squared plus c.
Good. Perfect.
Sweet.
Yeah. Yeah, these
are
a
lot easier when you recognize
the on these. There's a beauty in it that all these super complicated looking things, and they all go together, and you frequently have an answer that's got a trig function and a natural log function and a polynomial and everything. So,
right.
But yeah, in terms, I'll let you go. But that one, I'm almost certain that is going to be integration by parts, and it's going to require a second iteration. In other words, the first part of it's going to leave you something like that still after you're done with the first part. And then you'll have to do the second iteration to get rid of that last integral sign.
Right. And I think 6, I ran into the same problem.
Yeah, 6 is going to be worse because it's x to the third. So it's going to take 2 iterations or 3 iterations.
Right.
And so you end up with an answer that looks kind of like this times something. And then you have to redo the something. So then you end up with an answer that looks like this. And then you have to do another iteration. So you end up with an answer sign that's usually got about 6 negative signs in it.
Right.
And you got whatever that is, plus c. Okay?
Right.
But the hardest thing with those kind of problems is keeping track of all your negative signs, and make sure you don't drop a negative sign so that you turn something positive that's supposed to be negative or vice versa.
Okay.
Okay?
Okay.
All right, John. I will talk to you later, and please, if you can, try to get me material 2 hours in advance is because sometimes I'll be working for the hour in advance of your session. And
Okay.
it's really helpful to me if I just can look at it for 30 minutes. That's all it took me. After we've
Okay.
finished our session, I looked at it for 30 minutes and realized, oh, I got to use this technique on this, this, and this, and this. So
Okay.
advanced notice makes for a much better tutor.
Okay. Yeah. So Wednesday we canceled. I already paid for Wednesday and today, so I'll just reschedule another one for sometime this week.
That's
fine.
I'm
just not sure which day yet, and I'll send them the morning of. I'll just make sure to send them the morning of, so you have plenty of time.
Here's my schedule for the rest of this week. Yeah, this is Monday. So I'm not really very busy in the afternoon. My mornings are going to be Wednesday and Thursday. I'm going to be tied up. But
Okay.
in the afternoons, any time is fine.
Okay. Yeah, it'll probably be more like Thursday or Friday, depending on sports, after school sports.
Sounds good. And just as a reminder, if you make a session and you want to cancel it, you get a confirmation email whenever you schedule a session.
Okay. Yeah, I've been getting it.
And that email has a cancel link.
Okay.
So if you open up your confirmation email and click on that link, that cancels it automatically.
Okay.
Okay?
Okay.
All right, John. Talk to you later.
Talk to you later. Thank you so much.
Sure. Bye-bye.